Hello and welcome to another live stream of Chemistry 223. This is week 7. I hope you're all having a great term so far. Got a few more weeks left in this term, and let's talk about what we're going to talk about today. Today we're going to talk about oxidation numbers and um, galvanic cells, as well as kind of the different cell notations of galvanic cells and how to write them down and do that. First, let's talk about a little bit of the links and services we provide here at the Learning Center. So here's a link in the chat for the Learning Center. That's www.pdx.edu/learning-center/tutoring. You can definitely find out any of the services we have there, which includes academic counseling and tutoring for various different subjects. You can also check out the Pinji app and sign into that to see a schedule of all of our great tutors that we have here and schedule an appointment with them. You can also follow the Learning Center on Facebook and Instagram. The links are going in the chat for there. Just stay in touch and get notifications anytime we provide new services such as this live stream and other things like that. Also, definitely check out our recorded videos on the Learning Center's YouTube page. And you should be able to get to that through the Instagram or Facebook links. Also, just search YouTube for Portland State University Learning Center, and you should see a playlist for the Chemistry 223, and you see all the past videos that we have there for that. So let's get started today, starting out talking about oxidation numbers. So oxidation numbers are essentially talking about the relative charge that a certain atom has within the species that it's in. And when we talk about elemental atoms, they have an oxidation number of 0. These elemental atoms are stuff like, you can think of it as copper, Cu, solid, gold, solid, etc. Anything that's kind of in its pure state, it's not ionized in any way, shape, or form, there's going to have an oxidation number of 0. So that's silver. Actually, gold is Au, and so on and so forth. So any of the elemental charges, they have an oxidation number of 0. But when we have these atoms mixed into a molecule or they're ionized floating around in an aqueous solution, then they have an oxidation number which is equal to their charge. So I can say atoms in a molecule or solution have an oxidation number equal to their charge. So some relative examples of that would be like copper 2 plus in aqueous solution, silver plus in an aqueous solution, so on and so forth. There's lots of different ionized metals that float around in there, and anytime they have a charge associated with them, for example, this copper 2 plus would have an oxidation number of 2, and silver would have an oxidation number of 1. And there's a lot of these different ions we see floating around in there, and anytime we go from like a solid with an oxidation number of 0 to a copper ion, for example, solid copper to copper ion, we say that's a redox reaction. So it's an oxidating reaction because it's losing electrons. It goes from a neutral charge to a positive charge, which means it has to lose electrons in that process. So we call that oxidation. I'll say that's the loss of electrons. And it usually means that from the initial state to the final state, the atom has gotten more positively charged. So, for example, that if you have a copper solid turning into copper 2 plus, it would also have 2 electrons. Let's write that proper, 2 in front, E minus. And you notice that we have a balance of charge on both sides of that equation now. Where on the left side we had neutrally charged, on the right side we have that copper 2 plus, we have to add to that 2 negatively charged electrons, so the net charge on the right side of it matches the net charge on the left side. We could also see this as like an iron 2 plus, which can be aqueous, and that would turn into, let's say, iron 3 plus plus an electron. And this is also aqueous. So you notice in this case, our iron was charged and had an oxidation number of 2, but it moved over and got an oxidation number of 3, and in doing that, it shed an electron from it as well. So these are different examples of oxidation. When we talk about reduction, it's kind of the opposite effect happening. So for reduction is when you would have, we would gain electrons. Or we think of it as it's becoming more negatively charged, or going from a positive to a neutral is another version of becoming more negatively charged. Anytime we're gaining electrons in that process, it's going to happen to be a reduction reaction. And some examples of that is kind of just the opposite of what we had there. If I had copper 2 plus, then I would have to add 2 electrons to it, and it would produce a copper solid. Or if I had like silver plus, I could add 1 electron to that, and we would end up with a solid silver. Just some examples of reduction reactions. They're going from a positive charge to a neutral charge in these situations. Notice that in a reduction reaction, the electrons are a part of the reactants, while in an oxidation reaction, the electrons are more part of the products. And you're going to see that's a common thing, usually because of how those electrons have to move. By losing the electrons get split from the reactants and forming the new products. They're kind of floating around. They've lost those electrons. In the reduction reactions, they start off positively charged, and we're adding that electron as a reactant to create this neutrally charged reduction product. And since most redox reactions, pretty much all of them, are going to incur in water that we're going to deal with, we can assume any time that we're dealing with these, that oxygen, so O, has a charge of -2, I'm going to say 2 minus, and hydrogens have a charge of +1. And this is useful when we talk about balancing our redox reactions, which is what I'm going to go into next. Let's right over here. So for balancing redox reactions, there's a certain set of steps that we can basically follow to make sure we get this in the correct order. Usually it has to come with starting out with just these basic half reactions, looking at how the reaction starts and what that redox reaction or the oxidation or reduction is going on. And then we add into it water for all the oxygens that we might need in that reaction, and then balance it with hydrogens. So let's write those out. And then we can add our electrons at the end. So the first thing we do is write a skeletal equation for the oxidation slash reduction. TI, I had it right. And these we call half reactions. And this kind of looks like what I did on this previous page here. These are kind of examples of those half reactions. We're not looking at the full reaction of things. We're just looking at how does copper change. It goes from a solid, in this case, to a +2, and it produces 2 electrons. That's kind of the half reaction of that oxidation. Similarly, when the copper or the silver, in this case, is we add electrons to it, it's getting those electrons. It's a reduction reaction. So those are the type of half reactions that we would add at that first stage of that balancing. It's just doing that. At the second stage, we want to balance each half reaction for oxygen by adding H2O. And we do that, we were just balancing those reactions by adding oxygen in anytime we need to. And we do that for kind of the charge balance between everything. A lot of times those electrons have to come from somewhere, and since they're floating in an aqueous solution, the O is going to be a part of that reaction. Then we balance it. First, I guess we balance it for everything besides hydrogen and oxygen. Let me move that down. Sorry, I skipped a step. Balance reaction for all elements besides oxygen and hydrogen. The third step is balancing it with the oxygen in there. And then the fourth step is then balancing the hydrogens, the H plus in the half reaction. Once we do that, we can add basically the electrons just to balance the charge on either side of those. So now we're going to add electrons to balance the charge. And this has to be done to make sure you have the same charge on the reactant and product side of the reaction, because you can never have a difference in charge. We can never lose those things. Worst case, we're losing them in the form of electrons. We have to note that on the product side, or we're gaining them from gaining electrons. We have to note that on the product side. So the sixth step is to just multiply one or both of those half reactions so the number of electrons consumed is equal to the number produced, because we need the same number of electrons to be consumed as produced in this whole situation. So we multiply, say, reactions. So number of electrons consumed is equal to the number produced. And we're looking at the comparison between the two half reactions. Really, we want the number produced in one half reaction to equal the number consumed by the other half reaction. And then we add these reactions together. Just kind of adding the products on one side, adding the reactants on the other side, and canceling out any common values we have between the products and those reactants. At any time, if it's taking place in a basic medium, we can add OH minus ions to them. If it's taking place in just to neutralize any of the H plus ions that might be added. So in this step here, we added a bunch of H plus ions in there. So that's fine if it's the solutions or reactions happening in an acidic condition. But if we know it's happening in a basic solution, we have to add OH minus to it. So the last step, and this is conditional, if solution is basic, add OH minus to balance H plus. So let's go through an example of this and this is when I pulled out of the textbook, writing a balanced equation representing the reaction between solid copper and nitric acid to yield aqueous copper 2 ions and nitrogen monoxide gas. So the first step was to write a skeletal equation for the reduction and oxidation half reactions. So start with the reduction. The reduction reaction, that's where it's gaining those electrons. So we're going from just to solid copper is Cu solid, nitric acid is going to be HNO3, and then aqueous copper 2 is going to be Cu2 plus aqueous, and the nitrogen monoxide gas is going to be NO gas. Just to make sure we know the compounds that are going into these, we can then start to see what the reaction is going to be for these things. So the reduction reaction is taking this HNO3, this nitric acid, and it's aqueous because it's an acid, it's floating in water, and it's going to produce this NO gas. That's kind of that basic skeletal structure of the reduction reaction. The oxidation reaction, that is going to be the copper. So copper goes from a solid to this aqueous 2 plus ion. So we can write that out there. Now step 2 was to balance each of those half reactions for all the elements except for hydrogen and oxygen. So looking at these, they're already mostly balanced. We can see that looking on this side, we have NO3, so really it's just the nitrogen we're looking at. There's one nitrogen, and there's one nitrogen. We're ignoring the hydrogens, we're ignoring the oxygens for this step. Same with the copper, there's one copper there, there's one copper there. So we're pretty much happy with this step. So I'm actually just going to copy all this down. I'll just put no change. This is no change to half reactions. Because everything except for the hydrogens and oxygens are already balanced. Step 3 was balance the half reaction by adding oxygen, or adding 4 oxygen, H2O. So in this case, we're looking at this top reaction here, and I'll rewrite it. We have HNO3 aqueous produces NO gas. Well, we know that that oxygen's not balanced. We need 2 more oxygens in there. So we can add to that 2 H2O. By adding that 2H2O, which is going to be a liquid, of course, now our oxygens are balanced. We're ignoring the idea of the hydrogens being unbalanced. We're going to deal with that in the next step. But at this point, our oxygens are balanced. Looking at the oxidation, Cu, solid, that's already basically completely balanced. We don't need to add anything to that for oxygens or hydrogens. The next step, step 4, is adding those hydrogens. So looking at the balanced equation that we have so far, or the not so balanced equation, we have 1 hydrogen on the right side here. We've got 4 hydrogens, 2 times the 2 hydrogens on that side there. So we need to balance this with this. So we can do that by adding H plus on the left-hand side of this equation. So I'm missing 3 hydrogens, right? So I can do 3 H plus, and it's going to be an aqueous H plus. Basically, some acid is going to have to be in there, plus HNO3 aqueous. It's going to produce NO gas plus 2H2O liquid. So now we've got our liquids balanced. Our oxygens balanced with 4 on each side. Our nitrogens started out balanced, so we're happy there. And now we have our hydrogens balanced as well. So now we need to balance the charge of each side of the reaction. If we notice the charge of, the total charge of this side of the reaction. I need to write my copper. Cu solid plus Cu2 plus as well. So we need to balance both of these reactions based on their charge for this next one. So for 5, we're balancing the charge. The charge for this top equation here on this side is 3, plus 3, because we have 3 positively charged hydrogens. This compound is neutral at this point. This compound is neutral, and water is neutral. So we need to add 3 electrons over here on this side to balance out to make it neutral like the right side here. So if I rewrite that, 3 electrons plus 3 hydrogen plus aqueous plus the HNO3. I'm just rewriting this side here. And the main thing I've added is I've balanced this side of the equation, because now that's a neutral charge. We would do the same thing with the copper. The copper solid produces this copper 2 plus, but we need to add, this is aqueous, we need to add to that 2 negatively charged electrons, because the copper 2 plus needs to be balanced with 2 electrons to make it neutral like the left-hand side of the equation. So now we want to try to make sure that we're balancing the number of electrons on the first equation with the second equation. The electrons produced needs to equal the electrons created or consumed. So in this case, the electrons consumed are these 3 up here, but we're only producing 2 electrons. So that we don't have enough electrons that we're producing to consume the other ones, and vice versa. So what we can do to that is multiply them by the the least common multiple of them, or to get the least common multiple, least common factor. So in this case, we're just multiplying this top one, this whole equation, multiply everything by 2. This bottom one, we multiply everything by 3. I can do that by, there's 3 electrons there, so I know I have to multiply this by 3. There's 2 electrons there, so I know I have to multiply those by 2. Doing that, I can see that this turns into 6 electrons plus 6 hydrogen plus aqueous plus 2 HNO3 aqueous, which produces 2NO gas plus 4H2O liquid. Doing that similar thing to the bottom, we end up with 3 copper solid, which produces 3 copper 2 plus 6 electrons. The last step is to add the 2 half reactions together. In this case, adding them together, first we want to look at kind of the product or the reactants there and the products here. Are there any common values we can cancel out? And the electrons are always going to be something you want to be able to cancel out of this, because the electrons just move around within this reaction. They're not usually a product of the reaction in the final end of everything. And then we just write all the reactants together and all the products together. So writing that out, there's going to be 6H plus aqueous plus 2HNO3 aqueous plus 3 copper solid. Those reactants will produce 2NO gas plus 3 copper 2 plus 4H2O liquid. And this should have been aqueous, and so should this. So now we basically have our final reaction. And the last step is to basically check, this is number 7. Does this happen in a basic solution? And if it does, we need to balance the H plus with the OH. In this case, it's happening we're adding nitric acid to it, so it's going to be more of an acidic solution. So we don't need to do that last step. And this ends up being kind of our final reaction for it all. I'll put a big box around it. There it is. That's the reaction that's actually happening. And see, it seems like a lot of steps. We kind of went through a bunch of them there. But really, I'm taking it one step at a time and breaking it down. We write our half reactions. These are the start and end reactions and what charges they are. Now, this is the reduction. This is the oxidation for them. Then we break it down and we try to make sure everything's balanced, ignoring oxygens and hydrogens. Then we add in the oxygens first. We add those in the form of water. And we do those first because with that water comes hydrogens. So if we did hydrogens first, we'd have to do hydrogens again and balance everything. So we balance those oxygens first by adding water to it. Because this is an aqueous solution, it's going to get its oxygens from water. Then we add in those hydrogens to them. Basically, how acidic does this solution have to be? And those extra hydrogens floating around in there will kind of balance the hydrogens on the other side of it. Then we add in those electrons. And the electrons are the key part because that's what's happening in this redox reaction. The electrons are flowing from some of the reactants to the products or vice versa, depending on which direction it's going, if it's oxidizing or if it's reducing ultimately. The last step is to add all those two equations together into one kind of net equation for this reaction. And that gives us this long ass thing. And usually we're able to cancel out the electrons when this is happening. So we get this nice long equation at the end of it showing how the reaction is happening and what the oxidation and reductions are going through. So let's move on to the galvanic cell. I got a nice diagram here of the galvanic cell. I'm going to kind of make a bunch of notes on top of that. But let's talk first about what the galvanic cell really is. And really it's just it's a use. It's a way that makes these redox reactions really useful in creating this electrical current flowing through them. And this electrical current is essentially the flow of electrons from one side to the other. And they happen because of this transfer of electrons in this redox reaction, the spontaneous flow of this. It only happens in spontaneous redox reactions. So I can say, oops, let's draw with the right. It's a redox reaction which causes a transfer of electrons through a circuit. But when I say circuit, I basically mean there's a path of the electrons flowing this way from one to another. It creates this flow of electrons. And in electronics, we call that a circuit. It's any path for electrons to travel, which produces, I'm going to skip over to the other side here. Maybe I'll just move this down. Producing an electrochemical cell. So that electrochemical cell is really what we're talking about. It's basically a battery that's happening. It's a really basic battery using two solutions where, in this case, we've got silver nitrate solution over here and copper nitrate solution over here. The copper nitrate solution has in it a copper anode, this copper solid metal sticking down into the solution. The solution on the right side has a silver cathode, okay, this silver bar solid sticking down into there. And we have a solution of silver nitrate and copper nitrate. And in between, down here, there's this salt bridge. This salt bridge is really sodium nitrate. That salt bridge is going to act to kind of balance the chemical charge within those baths, as these solutions, while this reaction is happening. And the anode here is connected through a wire to the cathode. So we're going to kind of break down what's all happening in this. So as this reaction starts to happen, just like we talked about previously, the silver, the solid silver, is going to go through a oxidation reaction, right? Because it's going to lose some of its electrons, and once it loses its electrons, it becomes copper 2+. That copper 2+ is going to become aqueous. It goes from a solid, because a solid copper is not soluble in water, but copper 2+ is because of that charge. So it's going to be floating around in that solution along with these nitrates that are here. And as they float around in there, more nitrates are going to come out of this solution. So I can start writing on here, this CO2 is, or Cu2+, is created by that oxidation reaction on this side of the equation. And this nitrate, NO3, is going to flow out of the salt bridge into the solution to balance that chemical charge. The charge on that left side wants to stay the same. So it's going to, that salt bridge releases the negatively charged anions, anions, to flow through there to keep us a balanced charge over here. But when this became copper 2+, we lost electrons. There's some electrons that were here, and they took off down this path through that circuit. And they followed this circuit around, ending up over here on the silver side. So now we have these electrons floating in there, and this silver is electrically charged. It's got these charges, and since opposites attract, the silver ions get attracted to those electrons. And when the electron combines with that silver ion, neutralizing the ion, becoming a reduction reaction. And this silver forms silver solid on the surface of the solid silver. So the solid silver actually grows a little bit. Over here, the copper is actually shrinking a little bit. Eventually, this copper will actually kind of wear down into a tip if you leave it in there for long enough, if you have a strong enough acid mixed in there. But usually, it kind of uses up all of that it can before all that happens. So when this silver bonds to that silver and deionizes, it needs to balance this charge as well in this solution. And it does that, if I can spell, I wouldn't be a scientist. If it does that by releasing sodium ions floating in there, and they're in an inert ionic structure, it's just there to balance that charge in that solution as well. So we end up with that balanced solution. The salt bridge is really used for counter ions. And they get fed back into the solutions. This porous plug is to make sure they don't just they don't just bleed into it. They have to actually have a pretty strong attractive charge to get through them. And then the flow of electrons, these electrons, like I said, flow along this into here, which causes those silver ions to bond to them. And that's the basic idea and theory behind that galvanic cell. And there's some notation for some of these, for these types of reactions when we write them out, because we can use different types of metals for this. We can use different anodes. The part that gets oxidized is called the anode. Part that gets reduced is usually the cathode. And in this case, we call this an active electrode. These are active. And what I mean by active electrode is the metal electrode that's going down in here itself, it's actually part of the reaction. Sometimes we use inert electrodes, such as palladium or platinum, to transfer those electrons into our solution and cause that reduction reaction within the solution. So it'll go from like a +4 to a +2, and that palladium is used to, or I'm sorry, the platinum is used to just transfer the electrons down. So the notation that we use for this, do I have space over here? Yeah, I think so. This is cell notation. And if I were to write out that reaction for this galvanic cell, notice we have copper 2 turning into copper, or we have copper solid turning into copper +2. We have silver plus turning into silver solid. So we can write out that whole equation. I'm just going to write it out up top. Plus, say silver plus aqueous. Those are basically producing copper +2, aqueous plus silver solid. To balance the charge of all of these, I'm going to need 2 on that side because I have a +2 over there, which gives me 2 on this side as well. Zoom in a little bit. So that's the basic chemical reaction that's happening, but that's not cell notation. To get it into cell notation, we write it in a specific way so we can see the different stages and phases of the cell as it transfers. So I would start by saying each half cell is represented by its chemical formula. An example of this here, for this type of cell, the chemical formula is really just this copper and this solid silver. So I'm going to write that copper on one side, and usually the anode goes on the left and the cathode goes on the right. So I'm going to write the cathode over here, like that. So that's how we start things off, just by writing each half cell represented just by its chemical formula. And then we talk about the interfaces, which are represented by kind of a vertical line. Okay, which basically just look like that. I'll put little quotes around it. Just a big long line. And we can write those out. And the interface tells it like what happens with the copper. The copper in this case goes into that solution with that copper nitrate. So I can write that Cu solid interfaces with Cu copper nitrate, NO3 2 aqueous. Going from the right side, I can say silver solid interfaces with silver nitrate. Big O. And we're still keeping them separated at the moment. We combine those together with kind of a double line in the middle. And then basically the last step is to write it kind of from left to right, anode to cathode, and then separating it by that double line. I like to think of that double line representing the salt bridge between them, because that salt bridge kind of feeds both of them back out. But what that salt is made out of doesn't matter nearly as much, because it's usually just going to be some spectator counter ion balancing the charge of both of those solutions. So last step, beginning with anode, write all identifying phases and interfaces. And then I can just say end with the cathode. And remember that the anode is going to be our oxidation. The cathode is going to be our reduction. And remember, the oxidation is losing the electrons. So it's going from neutral to positive, or it's going from positive to more positive. Where the reduction is gaining those electrons in. So it's going from positive to neutral, or it's going from neutral to negative, or even say positive to less positive. Those are the different types of reactions you might have. But always, if you're gaining electrons, it's going to be reduction. If you're losing electrons, it's going to be an oxidation. So let's try this out in an example. We got two examples we can run through. So here we have a galvanic cell, which is fabricated by connecting two half cells with a salt bridge, just like our normal diagram said. One of which is a chromium wire is immersed in 1 molar of CrCl, or CrCl3 solution. Another with a copper wire immersed with CuCl3. Assuming the chromium wire function as an anode, the chromium functions right. The schematic for the cell, along with the equations for the anode half reaction and the cathode half reaction. So looking back on what we just talked about, we always begin with the anode, work our way to the cathode. In this case, we know, just writing the chromium, which is Cr, we write on the left side. And then on the right side, we would write our copper. That's going to be a solid as well. So we can then write these half reactions for everything. So the anode, this would be, again, the oxidation reaction. It's going to lose its electrons. So we know that some chromium solid has to produce, and it says here chromium Cl3 is what we're looking at. So the charge for chromium, after this is all said and done, is going to have to be a +3 to balance the 3 negative charge chlorines on the other side. So, because each of those chlorines has a -1 charge to it, adding 3 to that gives that chromium in that molecule a 3+. Aqueous. We know that. And then, because of that 3+ to balance the electrons, we can add to that 3 negatively charged electrons. We know the cathode, in this case, is going to be the copper 2+. Then we know that because here is our copper chloride, copper 2 chloride for that matter. So we know that we're going to have copper 2+, plus, or I should put aqueous, plus 2 electrons. It's going to balance out to make copper solid. Okay. Last time we had copper working as our anode. This time it's working as a cathode. And that's just the way that the transfer of electrons is happening in this case. So if we multiply to make those number of electrons lost and gained, because we notice here we're trying to balance these electrons. Here we've got 3 electrons. Here we've got 2 electrons. We need those to match. So to match those, we need to do some multiplication. Multiply this whole side times 2. Multiply this whole side times 3. Just the 3 came from there. The 2 came from there. And that's how we can figure out how much we have to multiply it by. Sometimes you can find the least common multiple of those 2. Or least common denominator of them to get the right number, but you can always just multiply by the other ones. You might end up having some multiple of the real reaction. So if you have some common multiple in your final thing, you can always cut it down. But adding these together, multiplying them together first, we would get 2 chromium solid producing 2 chromium 3+ aqueous plus 6 electrons. The cathode reaction can be 3 copper 2+ aqueous plus 6 electrons produces 3 copper solids. So now we can combine these two equations into one final equation that we have. Notice we cancel out the electrons because we have the same number as reactants and products, so they end up being basically a spectator. And this leaves us with 2 chromium solid plus 3 copper 2+ aqueous is going to produce 2 chromium 3+ aqueous plus 3 copper solid. And that's it. So, I mean, right there, we balanced our chemical equations and everything else like that. And we can also write out as a galvanic reaction, kind of in that cell notation. So, in that cell notation, move back up a little bit so we can see right in blue. We started out with that chromium solid on this side. It went through this kind of buffer of that chromium trichloride or chromium 3 chloride. So I can say CrCl3. And if we know the molarity of that, we can actually put that molarity in. It's telling us that molarity So I can write it as 1 molar CrCl3. There's my, what I call the salt bridge, kind of the interface between one side from the other. The molarity of the other one is also 1 molar. This is copper CuCl2, and that's interfacing then with copper solid. My S turned into a 2. There you go. And that's kind of the cell notation for this reaction. So let's try another one. Here they're going to give us that chemical reaction, but we need to figure out the right cell notation for everything. Notice in this case that we have Sn2 plus and zinc 2 plus, Sn4 plus and zinc solid. So the zinc goes from a solid to an aqueous ion. So it's going to be acting as what we call an active, what do I call it? Active, can't remember the name for it now, electrode. An active electrode. The zinc, so it's going from a solid to an ionic, so it's losing these ions into the solution from the solid object. In this case, the Sn4 is turning into Sn2, so it's not actually ever a solid object, so it's not going to be one of our electrodes. So we're going to have to use some type of inert electrode for this, right? Need inert electrode. So for that, lose platinum. That's what they used previously. It's a good one. It doesn't really like to give off a lot of electrons in that regard. And we can then write out what's going on with these reactions. Looking at the one, it's always the anode as the start. And so the anode is the oxidation. The oxidation is the one that's losing electrons, which is going to be our zinc, because our zinc is going from a neutral charge to a positive charge, becoming more positive. So it's going to be losing those electrons. So on the left side, and I'll just write out the half reactions for them first. For the zinc, it goes from a solid, and it produces zinc 2 plus aqueous, plus must produce 2 electrons, balancing that charge on both sides of those reactions, right? And that's got to be our oxidation, which is the anode. The second one starts out Sn4 plus aqueous, and that's producing Sn2 plus aqueous. And the electrons are going to have to be a reactant just to balance the charge on both sides. So we have a 2 plus charge on the right side. We need to have a net charge of 2 plus on the left side to make sure that's balanced. And since the electrons are part of the reactants, we're gaining electrons on this compound, or this atom is gaining electrons. So we call that a reduction, which is the cathode. And for that cathode, since we don't actually have a solid cathode in there, the cathode is really our palladium, or our platinum. I keep saying the wrong word. Platinum is PT. So we can write this out now as our galvanic notation, our cell notation, saying that we start out with the anode, zinc solid, interfaces with, and they don't really tell us what it's interfacing with. So it produces some zinc 2 plus in aqueous solution. And there's some salt bridge in between there. There has to be to counterbalance that, but it doesn't really matter what we use as long as it has the right proportions to counterbalance that 2 plus charge. It's going to interface with the Sn4 plus, comma Sn2 plus. Here we have 2 different stages of that. Both of them are going to be aqueous, so I'm going to squeeze in an aqueous. And that interfaces through the platinum solid. And that's it. That's our basic notation for the cell. Just writing that out says that we have this galvanic cell. It tells us the type of electrodes we have in there, zinc and platinum. It tells us the mixture of solution that we have in there is going to be some zinc ions and some Sn+4 and +2 ions in there. And we just need to add that salt bridge to add the right counterbalance for things and figure out the right solutions to make for it. But a lot of those are just your spectator ions. They're not the actual reaction that's going on, so we don't mention them here in the notation. That's all I have for you today. I hope this helped you understand the idea of redox reactions and galvanic cells. Definitely, if you have any other questions, feel free to schedule a tutoring session with one of our great tutors through the Pinchi app. I always have tutoring hours on Monday afternoons from 3 to 5 and Fridays from 1 to 5. So right following this live stream, I have about 4 hours of tutoring hours. I would love to talk to you about chemistry or anything else that I can help with. Have a great week and enjoy yourselves.